This is Dr. Fred DePiro, and this video is about using the principle of superposition in circuit analysis. Our learning objectives are to apply that principle to analyze circuits with multiple independent sources. Prereqs are easy. We just need Ohm's law and familiarity with our basic DC circuit elements. Alright, so how can we use superposition for analysis? Well, what we're going to do is to activate sources one at a time, performing a separate analysis for each of those sources. We then sum the response associated with the individual contributions. Now this provides us insight, as well as a final analysis. It provides us insight as to how each source influences a circuit. To get started, we need to know how to deactivate each type of source, that is, how to turn off the ones that we're not using in the analysis process. So to do that, let's consider the voltage and current characteristics of our various elements, beginning with a resistor. Okay. Resistor is a simple case. The VI characteristics are a straight line with slope equal to the resistor value. Now, important to note here, and in contrast with our other elements, is that the ratio of the resistor's voltage to current is constant and well defined as the resistor value, irrespective of circuit conditions. Let's compare that to the case of a voltage source. So here we have a voltage source that's driving a resistor representative of the other circuit, external circuit conditions, are anything. Now the current through the source, we don't know it ahead of time. It depends on circuit conditions. It depends on this value of R anything. Okay? So what would the overall characteristic look like in this case? Well, it's going to be a straight line. And if there were more elements that were providing power, for example, then the straight line could go negative as well. It's going to be a horizontal line. Now, the point of operation of the voltage source could therefore vary. In one case, it might be operating here with this current, or here with another current, or here, anywhere along that horizontal line. That means that the ratio of voltage to current for that source is going to vary, okay, just as the slope of these lines varies. That's due to the external components, symbolized by R anything. Thus, there isn't a clearly defined value for this ratio here. That is in contrast to the resistor, and this is the case when the voltage source is on or active. So now, let's consider what the value of this ratio is when we turn the source off. We can visualize that case by taking a limit as we let the intensity of the source drop to 0. In this case, with that value approaching 0, the ratio of voltage to current for the source converges, and it converges to 0. That's irrespective of the rest of the circuit and whatever external resistance the source is seeing. This gives us insight into how to model a deactivated voltage source. Since the ratio of voltage to current for the voltage source that's off converges to 0, we can model that source, that deactivated source, as a resistor with 0 value, or simply a wire. Okay? So to analyze a circuit in this manner, turning off one of the sources, you might consider redrawing it. Replace that inactive voltage source with a wire. Then take a look and see if you can simplify the circuit, because having these shorting wires may effectively eliminate other components. Now, for a deactivated current source, we can follow the similar logic as to the presentation for a voltage source. For the current source, the ratio of V over I converges to infinity in the limit with the current source approaching 0. And again, that's irrespective of the equivalent resistance seen by that source. This gives us insight as to how to model a current source that is deactivated. We can replace it with a break, okay, or a resistor with an infinite value. Okay? So, again, to analyze a circuit with a current source that's off, consider redrawing that source and replacing it with a break or open. Then see if you can simplify the circuit as well. All right, so our approach then is to activate our sources one at a time, performing a separate analysis for each source, and sum the response associated with those individual contributions. To deactivate a voltage source, replace it with a wire. To deactivate a current source, replace it with a broken wire or open. Now, when can we use superposition? Well, in any linear system, such as our circuits, we can apply the principle of superposition and use it for analysis purposes. However, typically, superposition is used to complement an analysis by equivalent circuits. We don't need to use it when we're doing nodal analysis or mesh analysis because those techniques can handle multiple sources. Also note that we only deactivate independent sources. Dependent sources are not turned off in this process. Here's a quick example. Consider charging a battery. The source VA is used to provide power, and this source over here, VB, is representative of the battery that's being charged. Those could be analyzed using a single KVL loop to get a total current of 2 amps. Just for illustrative purposes, let's consider using superposition and activate the sources one at a time. Here we have the source VA on, do KVL there, we get a current of 4 amps. Here we have just VB on, do KVL there, and we get a current of -2 amps. Note that the contributions are all in the same direction so that we can readily combine them to get the total current via superposition just by adding IA and IB. And note this example illustrates the concept only. This isn't the quickest way to analyze this, but it shows how to combine the response of the circuit due to 2 different sources, okay, with only one active at a time. Okay, so our learning objective here was to apply the principle of superposition to analyze circuits with multiple independent sources.